Okay, picture this. You wake up, check the news, and bam, alerts everywhere about an asteroid. And not just any asteroid, but one with an unusually high chance of hitting Earth.
Yeah, that's definitely a scenario that gets the heart racing.
Right. Your mind starts spinning, you see these percentages, these probabilities, and then wait, they change. And then they change again. You're probably thinking, like most of us, what on earth is actually going on?
It's completely natural to feel a bit unsettled when those numbers jump around like that. I mean, without understanding the science behind it, it's hard to know what to make of it all.
Exactly. And that's precisely what we're diving into today. We want to pull back the curtain a bit, look at how scientists actually calculate these odds and, what those changing numbers really signify. Our source for this is a really interesting piece from space.com. It was originally published in The Conversation, written by someone right in the thick of this field.
Yeah, and our goal here really is to sort of decode that complex data, turn it into something clear, something useful. So you, listening, aren't just getting headlines about potential threats, but you actually understand the context, the nuance behind them, properly informed.
Okay, let's get into it then. So this specific story, it really kicks off back in January 2025.
Right.
There's an expert, Toshi Hirabayashi, whose job is basically defending Earth from, well, unexpected space rocks. And he gets this alert, Asteroid 2024 YR4.
And the alert wasn't subtle. It flagged an unusually high impact probability. We're talking over 1%.
Which sounds small, maybe, but in asteroid terms, that's huge.
Oh, absolutely. For something in space, anything near or above 1% is considered remarkably high. It definitely sets off alarm bells in the scientific community. Immediate attention required.
And this wasn't just a pebble either. What size are we talking about?
This one, 2024 YR4, was estimated at about 196 feet across. So 60 meters, give or take.
Okay, 60 meters. Help me visualize that.
I think roughly a 15-story building hurtling through space. So yeah, definitely something you'd want to keep a very, very close eye on.
You're not kidding. And keep an eye on it. They did. Because what happened next with the numbers was, well, you called it a roller coaster.
It really was. So after that first alert in January, with the probability over 1%, it actually went up for a bit.
Up. Higher than 1%.
Yeah, briefly. It peaked at 3.1% on February 18th.
Whoa.
But then, almost immediately, the very next day, February 19th, it dropped back down to 1.5%.
Okay, so up, then down. Still high, though.
Still highish, yeah.
Yeah.
But then, just a few days later, February 24th, it plummeted down to 0.004%. Basically, almost zero chance for Earth.
That's dramatic. A massive drop in less than a week.
Extremely dramatic. And just for context, by mid-June, the calculated probability for an Earth impact was less than 0.000000081%. So effectively zero, a clear miss for us.
Okay, so that's great news for Earth. Risk dropping off a cliff. But
Yeah.
You mentioned an interesting twist.
Right. Here's where it gets kind of fascinating. While the probability for Earth was tanking, the chance of this same asteroid hitting the moon started to creep up.
The moon? Seriously?
Seriously. On that same day, Feb 24th, when the Earth risk dropped, the moon risk went up to 1.7%.
Huh.
And it kept climbing. By early April, the moon impact probability reached 3.8%.
Okay, that raises a question. If it did hit the moon, what happens? Does stuff fly off and hit us?
That's a common question.
Yeah.
And yes, an impact on the moon would definitely eject material. Some of that could theoretically travel towards Earth.
There sounds like a but coming.
But our atmosphere is an incredibly effective shield. Earth has a thick atmosphere. The moon basically doesn't. Any smallish bits of moon rock reaching Earth would almost certainly burn up completely on entry. No significant threat down here on the surface.
Right, our atmosphere. Good old atmosphere. Okay, so
Yes.
let's back up a bit. How are they even calculating these probabilities in the first place? What's the actual method? It's not just guesswork, obviously.
No, definitely not guesswork. The core technique is something called astrometry.
Astrometry.
Yeah, it's the science of measuring the positions and movements of celestial bodies. Very precisely. We're talking accuracy down to maybe a few kilometers of uncertainty in an asteroid's position, even millions of kilometers away.
Wow.
But, and this is the crucial part, it relies heavily on having accurate observations. And not just one or two, but observations collected over a period of time.
So when they first spot an asteroid, they don't immediately know its exact path. It's not like calculating a single perfect trajectory right off the bat.
Exactly right. You
Yeah.
can't. There's always uncertainty, especially with the first few observations. So instead of one precise orbit, what the calculations give you is more like a cloud of possible orbits. a range of potential paths the asteroid could be
A
on.
cloud of possibilities.
Yeah. And the region in space that contains all these possible orbits is what scientists call the error ellipse.
Yeah.
Think of it as a sort of zone of uncertainty around the asteroid's predicted path.
Okay, the error ellipse, I think I get that. So the impact probability that's connected to this ellipse.
Directly connected. The impact probability essentially tells us, out of all the possible orbits calculated within that error ellipse, how many of them actually result in a collision course with Earth.
Ah, okay, so it's the fraction of possible paths inside that uncertainty zone that actually hit us.
You get it. There's the number.
Right. So we saw this wild ride with 2024 YR4's numbers. Up, down, way down for Earth, then up for the moon. What's driving those changes? It must link back to this error ellipse thing.
It absolutely does. It really boils down to the size of that error ellipse and how it changes as more data comes in.
More data shrinks the ellipse.
Precisely. Think about it. When an asteroid is first discovered, you only have a few data points, maybe just observations from one night.
Right. Not much to go on.
Not much at all. So your uncertainty is very high. This means the error ellipse, that zone of possible paths, is huge. It's spread out.
Okay, big fuzzy cloud of possibilities.
Exactly. And when that ellipse is really large, it's actually more likely to just sort of accidentally overlap with Earth's position in space, even if the asteroid's true path, the one it's actually on, is going to miss us by a wide margin.
So the early high probability isn't necessarily because it's likely to hit, but just because the uncertainty is so big that hitting Earth is one of many, many possibilities still on the table.
That's a great way to put it, yes. The large initial uncertainty means Earth is included within the broad range of possibilities.
Okay. But then you said the probability sometimes goes up temporarily. That still feels counterintuitive if they're getting better data.
It does seem weird, doesn't it? But think about what happens. As more observations come in from different telescopes, over days or weeks, the uncertainty decreases. That error ellipse starts to shrink. It gets smaller and more defined.
Right, they're zeroing in on the real path.
Exactly. Now imagine Earth is still located somewhere within that shrinking ellipse. As the ellipse gets smaller, the proportion of possible paths within it that actually hit Earth can temporarily increase.
Ah, so the total number of possibilities is getting smaller. But if Earth remains one of those possibilities, its relative chance goes up within that smaller set.
Precisely. It's not that the asteroid suddenly changed course or became more dangerous.
Yay.
It's that the refinement of the data confirmed that within the narrowing range of possibilities, an impact was still plausible, and perhaps even more plausible among the remaining options.
That is subtle, but really important. It's a sign of improving accuracy, not necessarily increasing danger in the long run.
Correct. And then the final stage, eventually, hopefully, they gather enough data. The error ellipse shrinks so much that it becomes clear the asteroid's path and Earth's path won't intersect. Earth falls completely outside the refined ellipse.
And that's when the probability plunges towards zero.
That's exactly when it plunges, which is precisely what we saw happen with 2024 YR4 regarding Earth. The ellipse shrank, refined, and eventually excluded our planet entirely.
That makes so much more sense now. It really paints a picture of the scientific process refining itself.
It does. But it also highlights a really significant human element in all this, which is communication.
Ah, yes. How do you explain all this to the public when headlines are just screaming, "Asteroid might hit"?
Exactly. Remember Toshihiro Barashi, the expert we mentioned? He noted that even when scientists were putting out accurate data, getting the public to truly understand what those shifting numbers meant was a huge challenge.
I can only imagine if you just see the probability number isolated without all this context about error ellipses shrinking. It must look terrifying and confusing. Why are they changing their minds? Is it getting worse?
Right. Just reporting that single probability value, especially when it fluctuates, can easily lead to misinterpretation, anxiety, maybe even panic. It lacks the crucial context.
So what's the solution? How do scientists handle this communication challenge?
Well, it's an ongoing discussion, frankly.
Right.
One approach is maybe sometimes wait a bit longer, gather more data to significantly shrink that initial uncertainty before making very public pronouncements, unless the risk is exceptionally high.
Temper the initial alerts a bit?
Potentially. Or another avenue is exploring new ways to communicate the risk. Maybe not just relying on that single probability number, but finding better metrics, better ways to visualize the uncertainty, providing clearer guidelines.
So it's not just about getting the science right, but about explaining it right. Finding that balance between giving an early warning if needed, but not causing unnecessary alarm.
That's the tightrope they walk. It's incredibly challenging.
Okay, so let's try and wrap this up for you, our listener. What are the key things to take away from this?
I think the main point is understanding how these probabilities come about. It's through this careful process of astrometry, creating this cloud of possibilities, this error ellipse.
And crucially, knowing why those numbers change. It's usually not the asteroid getting more dangerous, it's the scientists getting more certain about its path as they collect more data. The error ellipse is shrinking.
Exactly. Those fluctuations reflect refining knowledge. In most cases, like 2024 YR4, that refinement ultimately leads to the risk dropping dramatically.
Understanding that process, that science behind the headlines, really empowers you, doesn't it? It helps you read news about these things more critically, more calmly.
It absolutely does. You can see past the alarming numbers sometimes and understand the scientific process unfolding. It gives you context, which is invaluable.
And maybe that leads us to a final thought to leave you with. Thinking about these communication challenges we just discussed, given how complex it is to talk about risk and uncertainty, especially with something as potentially scary as an asteroid, what's the shared responsibility here? How can scientists better communicate, and how can we as the public become better listeners and interpreters of this kind of complex information?
That's a really important question. It's definitely something worth pondering. How do we build that bridge of understanding for future events?
Food for thought. We'll leave it there for this deep dive.